Hi, hello. My name is Monica Gracida, and we're going to start the stream about spectroscopy and the electromagnetic spectrum. Okay, hello. Of the people that are live right now, could you give me an emoji of how you're feeling today? How was your day up to now? Okay, maybe we don't have anybody yet. We're going to wait for one more minute. If you're live, give us an emoji of how you're feeling today. How has been your day up to now? Okay, whenever you are ready for the stream, could you please give me an emoji? Okay, we're going to start the stream. We're going to start the stream with a spectroscopy. Don't forget, I'm sorry, let me focus the screen. There. Okay, much better. Don't forget to follow us on social media. The stream of today is going to be about the electromagnetic spectrum, absorption and emission of photons. We are going to check the electronic levels in UV and visible light. We're going to check molecular rotations and vibrations according to the radiation matter will get. Okay, just a quick review about electromagnetic radiation. Electromagnetic radiation is energy that travels as waves through space. We have here an example of a standing wave. If anybody's watching the video, who can tell me what the letter A represents? Okay, the letter A represents the crest of the wave. The bottom section represents the throw. And then you can also get a wavelength from here. It's labeled on the bottom. Or it could be any point of the wave to any other point of the wave. We can also measure or check the amplitude, which will be from the resting point to the crest, to the highest point, or from the resting point to the throw, or the lowest point. We can also check the frequency, which would be how many waves per second it appears. So if this diagram occurred in 1 second, then we will have a frequency of 1, 2, 3 waves. Okay. Okay, this is the electromagnetic spectrum. I'm sure you're very familiar with it. We have the different types of radiation, from radio waves to gamma rays here. And we have the wavelength and the frequency down here. We can notice that the wavelength, as the frequency increases, so if it's many waves per second, the wavelength decreases. And the other way around, if the frequency decreases, the wavelength, the distance per wave, will increase. Okay, so we're going to practice a problem of wavelength and frequency. Imagine that you have these two waves that represent some sort of electromagnetic radiation. If they ask us which wave has a longer wavelength, well, obviously it's the red one because we can see the diagram right here. But then they ask us to calculate the wavelength. So this is the only information that we have. A way to do this is to divide this distance into the amount of waves that we can see here. And we see like from this point to the next. So 1, 2, 3, 4. 4 waves are being shown here on the red one. That's why we divide the distance that is given by 4. And we'll get a wavelength of 4 times 4 to the negative 4 meters. Don't forget the significant figures. If the given has 2 significant figures, we must give our answer with 2 significant figures. The green wave, if we count how many waves do we have 1, 2, 3, 4, 5, 6, 7, 8. Yes, so from here, one wave starts and it ends here to the next identical point. So that's why we're counting 1, 2, 3, 4, 5, 6, 7, 8 waves. We divide by 8 and we got this wavelength in meters. So that's the wavelength for both waves. Do we have any questions so far? Okay, moving on. Then we have the next question about the same 2 waves. Which wave has the higher frequency and larger photon energy? So of course we can see just by looking at the diagrams that wave B has a larger frequency. But if we have to calculate this, we're going to use the formula that follows. This is the formula: wavelength times frequency equals the speed of light. Why can we do this? Because all waves travel at the speed of light, and the wavelength and the frequency are, if one increases, the other one decreases, are proportional to each other. So we can use the speed of light to get either frequency or wavelength if we have the other one. Since we have a wavelength, we're going to solve for frequency and get the speed of light divided by wavelength. We substitute the values that we had, the 4 times 10 to the negative 4 and the 2 times 10 to the negative 4 for every wave. So the one that has the greater frequency, as we see on the diagram, is the green wave, the wind wave, and now we have the value of that frequency. 1.5 times 10 to the 12 seconds to the negative 1, or hertz. That's what hertz means. So for example, if you listen in the radio, the stations, the 107.7 megahertz, that's actually the frequency of the wavelengths of the radio waves. So that's that unit of hertz here. Okay. And then they ask us which wave has the larger photon energy. If they ask us to calculate that value, then we're going to use this formula. Change of energy equals to Planck's constant times the frequency. The Planck's constant you don't need to memorize. You're going to get it from the constants that are provided on the AP exam. So you will have it, you won't need to memorize. So then Planck's constant is 6.626 times 10 to the negative 34 joules per second. You multiply the frequency that you got previously, and your answer is 9.9 times 10 to the negative 22 joules. The seconds and the second to the negative 1 cancel each other. Any questions? Okay, we're going to move on. Okay, then they're asking us which wave has the greater velocity. Okay. Do you have a clue which one has the greater velocity? Sure, Joel. Yes. Okay. In this slide, we were calculating which wave. Well, the problem started this way. They're asking us which wave has the longer wavelength. So we use the data above to calculate the wavelength for each. And then they ask us which wave has a higher frequency and larger photon energy. So to do that, we solve for frequency on this equation, and we substitute the values, and we get that the green wave will have the higher frequency, which is obviously, if we look at the diagram. Yes, the link of the slides will be provided, you're right, after the stream is over. And then we can calculate the photon energy by using this equation. And I was saying a while ago that this is Planck, H is a Planck's constant, and you don't need to memorize because it will be on the constant values for the AP exam. So by doing this equation, you will get that the photon energy for wave B would be 9.9 times 10 to the negative 22. Okay, thank you for asking. Let's move on. Okay, then the next question is, which wave has the greater velocity? Can you answer that question? Which wave will go faster? Well, yeah, faster in speed. B, U? Okay, if we remember from the formula, from this formula, the wavelength and frequency are proportional because the multiplication of this gives you the speed of light. So the wave that has the greater velocity, it's not B because they're both traveling at the speed of light. So they will end up having the same velocity. Make sense? They're traveling at the same speed, but this one is more frequent and has a shorter wavelength. And this one is less frequent and has a longer wavelength. Inversely proportional, the wavelength to the frequency, but they're both traveling at the speed of light. Okay? Okay, the next question is that which type of electromagnetic radiation does each wave represent? And if we go to the values of wavelength and frequency that we got before, we can check these values on the electromagnetic spectrum, and we can notice that values of frequency on the range of 10 to the 11 and 10 to the 12 would be close to the infrared radiation. So we can say that both waves represent infrared radiation. So you compare the waves to the electromagnetic spectrum. So they're going to give you on the problems either the electromagnetic spectrum or specific values for frequency or wavelength. Any questions here? Okay. Why did we choose red? Infrared, yes, because these values, let's check the wavelength. The wavelength on the values of -4 meters. Okay. Okay, we don't have a specific value, but we can check if we go back to the values, the frequency on the values of 10 to the 11 and 10 to the 12, frequency values of 10 to the 11 hertz and 10 to the 12 correspond to this area. Here is the frequency values of 10 to the 12. So that is more, it's closer to the infrared section of the electromagnetic spectrum. Excellent. Let's move on. Okay, so they both represent infrared radiation. So you compare the values that you have with the values of each wave in the electromagnetic spectrum. Okay, so now let's move on to photons. The definition of photons: photons are packets of energy emitted as light. A particular photon contains a quantum of energy, and we're going to see why this is important in a moment. So the photons travel at the speed of light as waves. So we can also use the formulas of wavelength and frequency to use them for photons. Just as any wave, they will have frequency, they will have wavelength, and the higher the energy, the shorter wavelengths they will show, and opposite with lower energy, they will have the longer wavelengths. Okay, so why is this important? If electrons in an atom absorb photons of certain quantity of energies, they use this energy to jump. These lines are energy levels inside of the atom. So if they're in a particular energy level and energy is directed to them, the electron uses this energy to jump to a higher energy level. Okay, and then the original level of the electron is called the ground state. If you move it to a higher energy level, now it will be on an excited state. But electrons want to be comfortable, want to go back home. So they will jump back down to the ground state. And when they do that, they will emit photons of a certain energy. So if we measure that energy, we can measure we can determine how much levels did that photon jumped back to. If the electron receives a lot of energy, it will jump to much higher energy levels. And then on the way down, since this distance is longer, the photon emitted will have higher energy. Okay. In here, for example, what I did here was place the energy levels as concentric circles so that we imagine the atom. The nucleus will be on the center, of course. And if we add energy to this electron, the electron will jump from level 2 to level 3. And then when it jumps back down, that's when it will emit a photon of certain energy. Is this understood? Okay, so let's go back to this one. In this slide, what we are showing is, for example, in the range of visible light. If the electron was originally in level 2. With energy added, it jumped all the way to the 7th energy level. Then it wants to go back home to its ground state. When it jumps back home, if it jumps from a level 7 to a level 2, the photon emitted would be on the range of violet light. So we will see a violet light being emitted. And on the same way, if it jumps back down from the 6th to the 2nd energy level, a blue color, from the 5th to the 2nd, the yellow, from the 4th to the 2nd, an orange, and from the 3rd to the 2nd, a red. Now, if the electron was in the ground state in the 1st energy level, on the 1st energy level, then we won't be able to see it with our eyes because it's on the range of the ultraviolet radiation. If the jump down is from either energy level to the 3rd one, our eyes also won't be able to capture it because it's on the infrared portion of the electromagnetic spectrum. So we're just going to see the ones that jump back down to the second energy level, because that's the energy that our eyes capture as visible light. Any questions here? Okay. So let's move on. Sorry. Okay. The application for this, for example, an atomic spectrum will be formed when a gas, an element in the gas form, if you heat up an element when it is in a gaseous form and pass that to a prism, it will emit lights of different color. Every single element of the periodic table has its own specific atomic spectrum. This acts like a fingerprint for the elements. The application for this, it's, for example, fireworks. If you have, of course, everybody has seen fireworks. You see that each color is given by a different metal. So fireworks, they have the gunpowder mixed with specific metals. And when the firework is ignited, the metals turn into gas. So what happens? The electrons of the metal are being excited. They're jumping to higher energy levels. And when they jump back down, they will emit colors, their specific colors. So for example, calcium salts give the red color, copper give red, and that's how we can have fantastic variety of colors if we place the proper metal. Questions here? Okay, another application for this is to check or to understand or to learn about the atmospheres of distant stars. The light that this is a way for astronomers to check the atmosphere of distant stars. They check the light that comes, that is emitted from those atmospheres, and by comparing it to known elements, they can know which elements make up the specific atmospheres. So pretty cool as well. Any questions? Okay, we're going to move on. Okay, so now molecular rotations with electromagnetic radiation. Different wavelengths of energy or of light will alter matter in different ways. Microwave radiation has only enough energy to rotate the molecule. So this is only, okay, I brought here a molecule of water, well, a model, of course, of the molecule of water, which is a bent molecule. So when we place a food in the microwave or water, the thing that the microwave is going to do is going to make this molecule rotate into the same axis. So this rotation will heat up the molecule and will heat up the food or the particles that are around that molecule. So that's an application for the microwave that we have at home. That's how it works. It spins molecules into its X, Y, and Z axis. And water, since because of its bent shape, it's very easy to rotate into its axis. So that's why I don't know if you have noticed, but foods that have high content of water get heat up much, much faster than food, like, for example, a piece of bread that doesn't have much water in it. Okay. Sorry. I want to... Okay. Questions? Okay, let's move on then. Okay, so the previous one, the one that rotates, it's with, I'm sorry, microwaves. If we have energy on the infrared part of the electromagnetic spectrum, that energy is much, much higher. So it will cause the atoms to vibrate. We can have symmetrical and asymmetrical stretching, and we can have, it will cause the angles to shift and vibrate. I have here this diagram, which can help you understand how these vibrations occur. It can stretch, like imagine that the water molecule stretches the bond here, right? Stretches, or asymmetrical would be this one stretching and this one compressing. And then it could be bending by doing this, or rocking, both of them on the same side. And then it could be wagging or twisting. So it will affect the matter differently than just the rotations that we have with the microwave. Now, of course, matter can also have much, much higher frequencies, higher energies. For example, ultraviolet light. For example, if ultraviolet rays penetrate or attack or are exposed to DNA, that these molecular vibrations alter the DNA and they can mutate the DNA. So that's why it's dangerous to be exposed, for example, to ultraviolet or gamma rays for a long time. It's dangerous because it can even affect your cells. Okay, any questions here? Okay, we're going to move on. So, for example, if we have this problem, how would a photon with a wavelength of 2.22 times 10 to the negative 4 meters affect matter or manipulate matter? And they give us the frequency of microwave, infrared, and visible and ultraviolet. So what is the first step? What must we do? What must we do with the data that we have? How can we check this? Okay, the first step is to change our given wavelength to frequency. If we change this given to frequency, then we can compare to the frequencies given. So we can do that by substituting on the formula frequency equals the speed of light divided by wavelength. We substitute the values and we get this answer. Then this answer we compare, and it is still on the range of microwave. So if we remember, the microwave will only do rotation to the molecule. So the only thing that will happen to matter if it's exposed to this photon, it will increase the molecular rotation in matter. Any questions? Was this problem clear? Okay, how do you feel on these topics? Do you feel you can do a good job solving problems? In a level from 1 to 5, 5 being expert, I totally have it, I can teach this, and 1, I have no idea. How would you rate yourself? Okay, a little bit of practice, you will have 4. Excellent. So, okay, Santiago, you can practice a little bit more. I'm sure in your book you have plenty of problems. If you have any question, don't hesitate to contact me. I will place my email on the last part of the of the slides. If you have any questions about any problem, contact me and we can solve it together. Okay, any question about the stream? Nope, everything good? Okay, from my part, that's it. Thanks for your attention. I hope to see you next time. I'm streaming again on Monday about the problems of the photoelectric effect. And that's it. Okay. Make sure you join us at 5 There's a lot of stuff going on for chemistry, and it will help you a lot to do great in your AP exam. Okay. Bye. Thank you.